Can we just do a call out? Looks like UC Davis, San Francisco.
San Diego's here.
San Diego. Okay, great. Well, I think we'll go ahead and get started so we can stay on time. I'm so excited to be doing kind of a more unique presentation this time around. And we're really going to be dedicating the whole time to discussing the health effects of wildfires. We have a very special presenter. It's Dr. Ian Gilmour, who's joined us today. He's speaking from North Carolina. He's the chief of Cardiopulmonary and Immunotoxicology at the Public Health Integrated Toxicology Division in the Center for Public Health and Environmental Assessment at the U.S. Environmental Protection Agency, or the EPA. And we invited him to discuss the health effects of wildfire smoke. I think that this is a pretty timely topic because we're just now entering into what's poised to be another busy wildfire season here in California. We've got drought conditions. As everyone knows, there's just a lot of wilderness areas that are vulnerable. And we experienced a rather traumatic wildfire season last year in the middle of the COVID pandemic. And basically, let me just share a few slides of pictures from there. Because this is going to go down in history as like the biggest fire in Fresno County. This was the Creek Fire. It actually erupted over Labor Day weekend, so in early September. There's a beautiful lake called Shaver Lake in our county, and it's just right nestled inside the foothills of the Sierras, and it covers both Fresno and Madera counties. And you know, taken from the air, this thing looked like a mushroom cloud. This was actually a plane that flew by in the early days of the wildfire, and it created its own weather patterns. And it eventually lasted till Christmas Eve. So like I said, it was the worst disaster in Fresno County modern history. It was related to, you know, a lot of dead trees that are still in the Sierra Nevadas, as well as gusty winds. And then it had its own internal weather patterns that are still being studied. Things like fire tornadoes and rain clouds, which then add to the wind conditions. Overall, almost 30,000 people had to be evacuated, and over 1,000 animals. And we're talking about big livestock like horses and things like that had to be evacuated off the mountains. And we're still trying to study how the drinking water has been affected and how erosion and flood risks will be affected for many years to come. So this was a rather substantial event, and you know, it goes without saying that this happened in the middle of COVID, so it really diverted a lot of our resources from the public health side. But nonetheless, I think that we fared as well as could be hoped. And I'll just share some pictures here, probably familiar to those of you that have been around wildfires, but you know, this was all news to me, and it really just brought home. Just, you know, whenever things incinerate, it's not just wood. There's a lot of other things that go up in smoke, and it just struck home that you know, the things that people were breathing in were just a number of different types of hazards that they could be exposed to. This is just a quick graph about what happened to the particulate matter concentration. So there's different sizes of particulate matter. Including PM 2.5, which is thought to be the biggest hazard, but we'll hear more from Dr. Gilmour about this. And the particulate matter concentrations, the federal threshold is less than 35. That's what's considered, you know, on the healthy side. And here the concentrations went up into the 150 to 180 range right after the Creek Fire began. And then you can see that there's peaks and valleys here, which are really interesting. It's almost like the fire, you know, it expands and then consumes fuel, and then it stabilizes a little bit, and then it expands again. The firefighters that I spoke to really described its behavior as like breathing, you know, in terms of inhaling and exhaling. And you can sort of see that that's reflected in the peaks and valleys here with the particulate matter. But, you know, this was a hazy air that I'm sure everyone in California had observed in the late months of 2020, and something to really reflect on. But particulate matter is just one number, and I think that the story is actually much richer and much more complicated than just this single number. And that's really what I have yet to learn all about, but this is something that I got very curious about, just having to deal with this as the health officer for Fresno County, and just deciding, which of these thresholds would activate different alerts or advisories, or even required shutdowns of different activities, et cetera. So there's a lot of, I think, human health effects that are involved in whenever these PM concentrations start rising. And that's really what I wanted to discuss today. So I reached out, and Dr. Gilmour very graciously has agreed to give us a presentation about his work. And he's been working really for decades in this space, and he's done some amazing research that he's going to talk about. And hopefully we'll address the following topics today, but really whatever people want to discuss. I really want this to be hopefully an open-ended discussion about the components of wildfire smoke, the acute and chronic health effects, and then how do we protect both the first response personnel, the firefighters, the EMS workers, and also the general public that are going to be in harm's way whenever these wildfires erupt. So with that, I think I'll take down my screen sharing, and then I'll let Dr. Gilmour introduce himself and talk about some of the research and other links that are at the end of the packet that I sent out last week. Thank you.
Okay, great. Thank you very much. Well, welcome everyone. Let me see if I can figure this out now. Share screen. So I want to give you this one. Share. And then I'm going to put my slideshow on, and hopefully you will see. Okay, so do you see my big screen with my cursor?
Yes, we can.
Okay, great. Okay, well, thanks very much, everyone, and Rais for inviting me. Some of those goals are a little bit loftier than I think I can really do. I'm just a lab bench scientist. Wayne Cassio, who will be giving you a talk in a couple of days, is my center director, and Wayne is a cardiologist and physician, and from the public health and intervention perspective, I'm sure he'll be able to touch on that more easily than I can, but I'll give it my best shot. So my name's Ian Gilmour, as Ray said, and I want to talk about the comparative toxicity of smoke from different fuels and combustion conditions. So this has been the basis of some work we've done over the past decade. I do want to say that this presentation does not reflect EPA policy. We're lab scientists, and we leave that to the policymakers, but I can talk about regulations and PM levels and so forth. Okay, so the first issue, and you're all aware of this, is really where there is smoke, there are health impacts. This center graph, it's from Science in 2006, and this actually talks about climate and temperature change and how there's a relationship between the drying and the droughts that have increased over the past several decades and the incidence of wildfires. And it's very clear also that when there is a wildfire or smoke events, that there are increases in hospital admissions. This is from Sarah Henderson in Health Canada, but there are many other examples, including those from California. Over on the right, you can see this is EPA's Air Now website, where you can really look at time of flight, daily, or you can look historically at the air quality, either single pollutants like PM or ozone or combinations thereof, and you can actually overlay the wildfires. So this is a very important tool for health scientists and physicians who want to look and see the extent of their pollution and even perhaps see where it's going. I urge you to look at Air Now if you aren't aware of it already. And then finally on the left, this is Seeley Lake in Montana a couple of years ago during some wildfires. And, as Ray said, these levels reach what EPA would regard as hazardous concentrations. And this was for almost a month in Montana, where visibility was, down to, a couple hundred yards or if that, and literally hazardous conditions, for the exposed population. Now, you know, smoke is complex. You know, it used to be that smoke is smoke is smoke, but that clearly isn't right. As toxicologists, you know, we know that it has to differ both in chemistry and toxicology, which depends on the fuel and the combustion conditions and the atmospheric conditions at large. But regardless, you know, smoke is complicated. You know, when you just look at one, you've got particles, obviously. There are a huge number of gases, VOCs, metals, organic constituents. So it's a very rich mixture that's dynamic over time and space. This is one of the really premier reviews on wood smoke, biomass smoke, published in 2007 by Luke Nair. And the first thing I want to just illustrate to you, and I mentioned it just briefly there, was there are two phases. There are particle phase, because people think about PM, and then the vapor phase or the gas phase. So for example, carbon monoxide obviously is a gas. So you see it here, not in the particles. Similarly, let's see, you know, you have other components that, for example, this unresolved complex mixture that was extracted from the PM. So that was found in the PM, not the gas. But also there are a number of constituents or components that are found in both phases. So you have what are called semi-volatile components. And essentially they can move between the particles and the gas phase depending on the temperature and the humidity and the level of mixing. I think one of the things I want to just kind of illustrate is that it's awfully complicated. It's organic in nature. There's a huge amount of organic chemistry here, whether it's aldehydes, polyaromatic hydrocarbons, non-methane hydrocarbons, alkanes, you know, just this very rich organic mix, both in the particle and the vapor phase. Now, if we want to think about the relative toxicity of, say, wood smoke or biomass smoke, you know, the kind of most comprehensive analysis was done by my colleagues at the Lovelace Respiratory Research Institute, and they were funded by EPA as well as other partners for probably 15 years. And they wanted to know whether, for example, diesel exhaust was more or less toxic than wood smoke, or gasoline exhaust, or coal emissions. They also had plans to look at cooking fumes, road dust, and tobacco smoke, but you know, the kind of program project ended by then. But they did, you know, look at this in animal models, a number of different animal models: cancer, infection, inflammation, hypertension. And, you know, they looked at multiple exposure levels, 6 hours a day, 7 days a week for up to 6 months, chronic inhalation exposures. So really a hugely rich database. And, you know, this is some data from that effort. And the one thing that I want to point out is, you know, many of us get stuck on PM and you think about PM. This was actually controlled so the PM was the same level. And if we look at diesel, and I want to say they were shooting for maybe 50 micrograms per cubic meter or something like that. And here we have diesel, and this is the PM, this little slither of black. Here's the hardwood smoke that they studied, and here's coal. And they were about the same level. Gasoline actually almost gives no PM that's measurable in a modern gasoline engine. So they couldn't actually achieve this concentration of PM. But what I want to illustrate again is the range of different gases, such that here's diesel. You've got a fair amount of carbon monoxide, a lot of NO, nitric oxide, and NO2, and then some non-methane hydrocarbons. Looking at hardwood smoke, no NO or no NO2 to speak of, fair amount of CO, and some of the non-methane hydrocarbons. If we look at gasoline, a ton more CO, and you all as emergency physicians know, you know, if you're going to commit suicide, you know, the gasoline engine's the way to go, and this would show that. And this other mix. And then when you look at coal, really none of the other gases. So what did they find from toxicology? Well, they found that in this system, using a number of different models, that diesel was more toxic than gasoline. which was more toxic than hardwood smoke. And all of those were really more toxic than the coal combustion PM. So, you know, this kind of gives you this sense of relative toxicity. Now we're going to talk about wildfire smoke, and I would add that this was one fuel under one combustion condition. So it's not clear whether, you know, there is variation depending on the different biomass smokes, although I'll show you there is. Anyhow, I hope this just kind of shows you that kind of bigger picture from a combustion toxicology perspective. We got into wildfire smoke because we got exposed in North Carolina in 2008. They're really quite rare here, but we did have a peat fire. And Dr. Cassio will talk about this more, but you know, what we found, or at least prospectively what happened, was that during this peat wildfire in the eastern part of North Carolina, there were more hospital admissions for all respiratory, asthma, COPD, across the board really. And also there was an increase in heart failure in the exposed population. So we had both cardiac and pulmonary effects from this wildfire. We were actually sitting on Interstate 40, about 3,000 miles from where you all are, but the same road. And we were sampling PM, you know, to study the effect of PM at different distances from the road, and we were looking at different size fractions. So we were happily doing that when this fire arose. So we thought, well, you know, we've had enough of the near roadway campaign. Let's go do something more interesting. So here was this wildfire. It was burning down here in a national refuge. And we knew that the wind direction was predominantly from the south or the southwest. So there wasn't much space here. And in fact, it was quite dangerous. The roads were being closed. So we jumped across the Albemarle Sound and set up a sampling site here in Camden, North Carolina. And we sampled, you know, for a few months. I don't know if you can hear this, but this is a North Carolina thunderstorm on my skylight. We sampled for a couple of months. And what this shows here is this is actually an EPA monitoring site below or down, upwind of the fire, I should say. And there wasn't any real change in PM. But when you looked at the sampling site of Virginia Beach, you can see, you know, that there was an increase both in PM 2.5 and PM 10 during this wildfire event. And it was quite clearly coming from the fire. We actually segregated this into two different periods, which we called ENCF1 and ENCF2, they're depicted here. And we extracted those from the filters and we instilled them into mouse lungs to see if there was a difference in the relative potency of these two samples. And indeed there was. ENCF1, and this is the coarse fraction, caused more inflammation in the mice and more, a good bit more than when the fire was controlled. Same amount of PM, so this is more toxic. If we look at neutrophils, we see the same effect. I do want to point out that fine and ultrafine PM, you know, typically are less bioactive in the mouse lung than coarse PM, and we have a number of suggested reasons. The coarse PM's got more lipopolysaccharide, bacterial endotoxin, and also is more crustal in nature, which might activate macrophages. The interesting other observation was, though, we were taking the lungs out of these animals, or the hearts, and doing what's called a Langendorf reperfusion. And we're looking at development of left ventricular developed pressure after a hypoxia challenge. And the only particle that actually had an effect was the ultrafine from the wildfire, which was quite interesting. So we had this effect on the heart function. And also when we looked at the injury in the heart, we found more with this ultrafine fraction. So here we think that we actually recapitulated the epidemiology with a twist. We think that the ultrafine particles have the cardiovascular effect, and that the fine or the coarse particles actually had the pulmonary effects. And that was really the first time that had been suggested, that you know, within the mix you get differential health effects depending on the size. So this is the obligatory Larson slide, about why the dinosaurs really became extinct. But what it does is it leads me into a segue, because from that, I started thinking, well, that's peat smoke. What about other kinds of smoke? I mean, surely they're not all the same. We did get chemistry on those samples, and it was interesting. It wasn't exactly the same as other biomass materials. So we start to think about, well, I wonder if a forest fire and combustion conditions, smoldering versus flaming. Rais, I see your hands up.
Oh
Are
yes,
you
forgive
okay?
me, Ian.
Okay,
Can you just describe what peat is? I'm naive and I don't quite know exactly
sure.
what that means.
Yeah,
Yeah,
well,
sorry.
peat, yeah, peat is really a precursor to coal. So it's organic material that is compressed. Peat. Well, I'm from Scotland. We used to burn peat in fires, and the Irish still do it. It's actually very good for making Scotch whiskey, as well. But peat is essentially soft coal, simplistically. It's not received the pressure from the uh, you know uh, subterranean pressure yet, but it's a precursor to coal. Okay. Anyhow, and it's well, East Coast of North Carolina is very prevalent. There's a lot of peat in Russia. In fact, Russia have had huge peat fires that are almost subcontinental, in nature. Canada has a lot as well. Anywhere you're finding oil, and it's essentially compressed, degraded organic material. Anyhow, so we started thinking about the chemistry and the constituents, and the PM, of course, and the gas phase. So we wrote a grant. Well, and of course, one other aspect that's really becoming more of a concern is, like, not only do you have biomass burning, but houses and other synthetic materials are going up in flames. And obviously, the chemistry is going to change depending on some of the fuels that are burned in these systems. So our first proposal, we actually got funded through what was called the Joint Fire Science Programs, connected with the Forest Service. And we proposed that we would burn a bunch of different woods and fuels. We would figure out a way to trap them and make condensates. We would do a full chemistry analysis. And then we would do toxicity testing, either in mice or knockout mice or cell-based systems, and we would come up with a toxicity ranking matrix. We actually changed it. We moved to this tube furnace system that we developed, and you can line your fuel down a quartz tube, and depending on the temperature of this furnace, and you're going to see this in a moment, this is smoldering, and there it turned to flaming. And you see there's a lot less smoke there, because flaming combustion is more efficient combustion. You make a lot less PM, and most of the CO2 is converted to, or CO is converted to CO2. So right there, flaming and smoldering are quite different animals. And of course, wildfire has both. But if you choose one or the other, you're not going to have the full picture. So I just want to leave it at that for now. We also developed this really neat cryotrap system. The reason being that smoke is really sticky. If you have a campfire, you're out cooking hot dogs or marshmallows, you'll know that when you come in, you can smell it on your clothes for days, and it's sticky, but also you can't get off a filter. So we developed this cryogenic system by which we can draw the smoke into impingers filled with small beads, and we can actually do an acetone wash and get all the particles, as well as the semi-volatiles and possibly some of the volatiles, back into suspension. We proposed that we would look at different fuels that are relevant and prevalent across the United States. So we had red oak, which is kind of here, lodgepole pine for the West Coast. We chose eucalyptus, which is actually a surrogate for chaparral, which is very common in California. And then we had some pine needles, and the peat. Okay, so we want to test these different fuels and either the flaming or the smoldering. So this is some of the data. This is chemistry, first of all, and you'll see again, it's very organic in nature. These are the 5 different fuels. And one thing that will jump out is, well, when you flame it, you get more inorganic elements. Some elemental carbon shows up a little bit more, and ionic species. So, you know, there are some differences across the fuels. Another nice thing is that from a mass balance perspective, we could identify anywhere from 55 to 80% of the chemical species, which actually is quite a feat when you know, because quite a lot of this stuff is, you know, unknown. It really depends, you know, on how precise your measurement is and at what level of chemistry you want to do. But anyhow, the point is that it's very heavily organic, not unexpected, you know, and there are some differences between smoldering and flaming. We could go further down into speciation. You look at things like levoglucosan, which is a tracer for wood smoke, methoxyphenols, which are those nice rich aromatics that you get in like eucalyptus and menthol and things like that. And then PAHs, you know, of toxicological concern. It's interesting, and I didn't know this, but actually, if you flame or if you burn biomass at a higher temperature, you get more PAH formation, which is counterintuitive. You'd think this smelly smolder, you know, organic soup would give you more PAHs, but actually you need the higher temperatures to get the proper ring formation for polyaromatic hydrocarbons. Anyhow, that's kind of the chemistry. Again, we instilled these into mice and we didn't see any toxicology with the smoldering emission, but we did see that the peat and the eucalyptus were really quite toxic, or much more pro-inflammatory, if you like, than the other fuels, and also compared in the flaming versus the smoldering situation. My good friend and now newly retired colleague, I'm sad to say, David DiMarini, he's a world expert in cancer biology, and he serves on many international committees. David's great. He just retired last year, but anyhow, he's been my partner in crime for over a decade. And we found that looking at mutagenicity, which is, you know, a marker for cancer causation, that again, the flaming samples were more potent at mutating salmonella than the smoldering samples. One thing that I should add at this point is that, you know, smoldering is less toxic on a mass basis, but you have a lot more of it. In our hands, if you're burning the same fuel under smoldering versus flaming, 10 times more PM is caused or is emitted from the smoldering situation. So even though it's less toxic, if you're exposed to 10 times more, then perhaps that dose response is not, well, you kind of have to look at it both ways. And this is where David does his comparison. He actually looks at revertants, the salmonella changes or mutations per megajoule of energy or thermal energy. And when we look at it this way, we actually see that the smoldering emission is more mutagenic than the flaming, because there's more of it, 10 times more of it. But the nice thing is that he can then relate this back to other systems that he's studied in the past. So it provides a nice comparative metric. So this was some wood, what do you call it, cook stove stuff that we did, you know, with the developing countries. But he's also burned agricultural plastic and tires and really nasty things. And, you know, it kind of provides this very nice comparison about the extent of the mutagenicity based on, you know, the amount that's emitted. All right. Okay, so that was the first part where, you know, we studied ambient PM from the smoke, and then we started developing it. But installation into the mouse lung is, you know, somewhat frowned upon. It's, you know, obviously if you can do inhalation, that'd be a lot better. So we've since developed a system so that we can actually expose mice and measure some nifty things both during exposure and of course afterwards. So we had the same system, you know, and we can do all the different measurements of the gases and the PM and things like that, and we can expose these mice. And the one issue becomes, well, what are we going to compare? And I've already mentioned that when you smolder, you make a lot more carbon monoxide. So if I wanted to have the same level of PM from a smoldering and a flaming, the CO is going to be wildly different. And of course, that has its own physiological health effects, even at subclinical levels. So we decided to hold the CO and use that as a metric, and then just look at the differential effects of PM regardless of the concentration. So this is 3 of the fuels, peat, eucalyptus, and oak, at approximately the same level as CO. I think we were shooting for 60 or 70 ppm. And this is pretty good over 1 hour if you consider this is a combustion. Yeah, so this was the exposure. But then what you see, and I've mentioned this already, and this is my tenfold differential. So when you're holding the CO at the same level, this is the level of PM from flaming, and this is the tenfold higher level when you're looking at the smoldering at the same CO level. All right. This is carboxyhemoglobin, which you all are, I'm sure, very familiar with, and we kind of see the same. Well, it's not quite the same. We're holding the same PM level. I think that the CO was, or sorry, we're holding the same CO level. It was a little bit more in the smoldering, and that was somewhat reflected, you know, but it's about the same. You got carbon monoxide that you can pick up in the mouse lungs compared to air, not the mouse lung, mouse plasma. And this is in line with smokers' carboxyhemoglobin. So this is a fairly large meta-analysis, I think, where you see carboxyhemoglobin in the order of about 8%. You know, and we were 8 to 12%, you know, with these exposed mice. And this is immediately after 1 hour exposure, whereas obviously these are chronic smokers. What we found, similarly to before, was that, you know, we got inflammation from peat and eucalyptus. I just want to draw your attention to the fact that this is the flaming, and here's the smoldering. The smoldering PM was 10 times more, and yet the inflammation was about equal, which kind of enforces the fact that we think that on a mass basis, the PM from flaming is more toxic. And we saw that for eucalyptus as well. And really, there was no effect with oak. The air animals gave us a little bit of heartache there. Now, Steve Gavitt, another of my colleagues, Steve's a respiratory physiologist, small animal physiologist. And, you know, we got him involved because one of the things we wanted to do was measure lung function during the exposure. And also we wanted to look at the effect of filtration to see if we can differentiate the effects of the PM versus the gas phase constituents. So we engineered a filter into this. This is not the filter. This is my graphic representation. Anyhow, we filtered these guys. And this is actually a C times T graph, concentration times time. But I want to draw your attention to this red graph first. And this is breathing frequency during a 3 hour exposure to smoke. And, you know, it drops a good bit, you know, probably, you know, breaths per minute, you know, maybe less than a mouse is about 450, 500 breaths per minute. So this is an irritant response, so they'll drop it by perhaps a third. If we filtered the smoke, you can see that you had the same drop, but it was less pronounced during the middle part of the exposure. So filtration under this circumstance, you know, seemed to have some level of protection. These are C times T products. So if we gave them the same amount of PM over 5 days or the same amount over 5 weeks, and when I say that, that's the cumulative dose, then they really didn't do anything. So, you know, obviously concentration is more important than time under this scenario. And we're being asked this because, you know, if you're exposed to a high level for an hour, is that the same as being exposed to a lower level for a week, you know. So those are the kind of toxicological questions we're being asked, and even months, you know. So you obviously can't address that within some of these inhalation systems, but that's the first stab at it. Another colleague of mine, Eamon Farage, these folks are all in my group. Eamon's a cardiotoxicologist or toxicologist with cardiac interest. And he was studying heart pressure, and this is somewhat limited right now, but we hope to do a lot more of this. And he saw trends for, you know, as we increased, and this was using the Peat again, I think, we saw some trends for decreased heart rate, increased blood pressure, you know, and both during exposure as well as post-exposure. And they also do sensitivity to a aconitine challenge, so it's an agonist challenge to the heart, and they found some effects there. So there are some hints that there are cardiac effects. Again, this is just a 1 hour or 2 hour exposure, you know, to you know, the peat smoke, and we really don't know what would happen, you know, when we enter a more chronic phase. We assume that things might get worse. Okay. So I'll conclude with this part. I've got a few more snippets to go, but I think, you know, hopefully I've demonstrated that, you know, this combustion system that we developed, incidentally, this was somewhat developed in the 70s for the cigarette industry, you know, which is a little bit ironic, but, and of course it was the Germans that made it because they're so good at this stuff. You know, so we kind of found these old publications from the mid 70s that that describe some of these systems. And we obviously had to reinvent things and try and interpret them, but, you know, it was just interesting. So they used it for big tobacco-based research and understanding the chemistry of tobacco smoke. But anyway, you know, we've adapted it, I think, quite handily for biomass smoke exposures, and they're reproducible. You know, one of the hardest things when you're doing the toxicology of wood smoke is that you've all been at a campfire and it's crackling and it's flaming and going down, and the variability just kills you. And within a toxicology kind of situation, you know, we really need reproducibility, and we've found that here. It's also useful for this emission testing, emission factor testing, where people can actually look at different fuels and, you know, and get real analytical data from them for predictive modeling of different fuel types across, you know, the land. Anyhow, clearly the fuel composition and the combustion conditions, I think I've shown, influence the chemistry, the toxicity, and the mutagenicity. And with these circumstances, you know, we saw that peat and eucalyptus were more potent on a mass basis than, for example, oak. You know, it's kind of not rocket science, and intuitively you'd think it, but until you prove it, no one knows. They just say smoke is smoke. We can see that the smoke inhalation has significant effects on lung injury and inflammation, and as well as changes in breathing frequency and heart rate. Well, you know, we have these suggestions of increasing blood pressure and perhaps risk of cardiac disease. And we're really just touching the surface here, although, you know, we've got good plans to continue with this. And, you know, importantly, you know, we've studied filtration now under a variety of different conditions, and, you know, that's very useful for people that are in the field. You know, does filtration work? Well, it does. You know, it certainly knocks a PM down effectively. You know, the gas phase constituents, some depending on the fuel and again the combustion condition, it might not work, but, you know, it can work. And that's kind of some of the work that we're doing now to try and understand where and when filtration can be protective. Okay, so, you know, we've been doing that for a good while now, and actually the funding ran out, if I have to be, you know, so we were thinking about other things to do, and we got approached by our colleagues at University of North Carolina who were interested in military burn pits. And they actually got funding from the Department of Defense to study that, and we got written into the grant Young Ho Kim and myself. And I thought it was a win-win because I was seeing from the campfire and other situations where houses are going up and cars and sofas. And, you know, I thought, well, you know, this perhaps has you know, it's equally kind of relevant to wildfires. And of course, you know, trash burning and things like that. I mean, obviously it's frowned upon. It still happens, but this is kind of all the same stuff. It's plastic, it's cardboard, it's plywood, it's got different things in it, glue, asphalt, you know, but it's all these kind of synthetic materials. And the question becomes, well, you know, what's the toxicology of that? What's the chemistry of that? How does that differ to biomass? So, you know, this is kind of how we got involved with this kind of a back doorway almost. And interestingly, you know, the military have actually got a waste stream analysis of their burn pits. Now, you know, this is kind of a holistic breakdown. So, I mean, these are a number of different pits, you know, Afghanistan, Kuwait, Hawaii, DoD standard of all things. You know, but you see that paper and plastic and wood, you know, make up, you know, a fair amount of it, certainly over 50%, upwards of 60%. And the rest of it is like food, liquid, textiles. And then there are others, of course, you know, I mean, which might be ammunition. I mean, human waste goes in there, you know, so there's all sorts of stuff. But, you know, our thought was, how can we start? And again, getting back to the reproducibility of this, if we're going to study this, we have to kind of study it so that we can repeat it, you know, time in, time out. So we use this data to actually develop a fuel composition, looking at military grade plywood, cardboard, and a series of different plastics which come in different kind of species, if you like. And again, there was different composition of high and low density polyethylene and polystyrene, which we figured out. So we chopped all these guys up. And then quite often they fuel these burn pits or fire them with diesel. So we thought, well, let's add some diesel to this as well, and we'll torch that. So we did that. And, you know, we, again, you know, used our combustion tube furnace system to burn these, and looked again at many of the endpoints that I've shown you already, you know, in vivo toxicology as well as chemistry, and collected them. I must say that whenever we got the plastic going, it trashed these tubes. These $100 tubes were never going to be used again, you know, so it became a bit more of an expensive deal. This is, let me see here. This is some of our organics. I can't point the arrow and look at myself, but here we go. Okay, so I just want to give you the nomenclature here. So this is plywood smoldering on the left, and this is plywood smoldering with the filter. So if you filtered it, do you get any reduction? And you don't, because these are all VOCs. So these are the volatile organics. So you're not going to see an effective filtration. The next one over is cardboard smolder, and cardboard with the filtration. And, you know, we're seeing lots of pretty toxic compounds, and you're seeing that it's increasing. We get to the plastic, and actually, you know, we see a lot more of the organics, you know, of these various species. And filtration, actually, you got even more, which is interesting. And there are reasons why that would occur. And then this was the mix. So plastic clearly is the top dog when it comes to emitting VOCs, you know, when it's burned. This is the flaming plywood, either filtered or not, and the flaming cardboard, filtered or not. We have not been able to do the flaming plastic because it explodes. So, you know, you get an elaboration of gases that increase in pressure, and with the flame, it blows up. So we're trying to figure that out. It's, you know, we'll get there. It's just, you know, within the system, you know, we've actually managed to do the flaming things in an unpressurized system, but, you know, within the system that I've described to you today, you know, it's pressurized. So we've had a challenge with that. But I guess, you know, the main point here is, you know, when we're burning these things, we're getting a huge amount of VOCs, and plastic really, you know, and as you guys would know. Don't burn your plastic bottles, don't burn trash bags and things like that. But anyway, when we go back to the chemical analysis, and here's our plywood, cardboards, plastic mixture and mixture with diesel. Again, this is our smoldering and our flaming, and you see the flaming just rocks for PAHs and nitro and oxy PAHs. I mean, just huge amounts. You know, the mixture and the diesel was actually the highest because, you know, diesel on its own will make PAHs. You know, so again, this kind of illustrates that that flaming combustion is very potent, or at least creating many more chemicals that have great health concern. And with that, of course, well, what about the cancer-causing capability? Well, it's exactly the same. So the flaming, these species are very mutagenic. These are different substrains of Salmonella with or without S9, which determines whether the compounds have to be metabolized before they can become mutagenic. But across the board, this stuff, you know, with the flaming was highly mutagenic. And in fact, when we go back to David's revertants per megajoule of energy, we find that the plastic flaming smoke is on a par with the worst thing he's ever studied, which is burning tires. So, you know, and obviously there's a break here on the y-axis too. So, you know, I mean, this is, I suppose, predictable, but, you know, people haven't really studied this or measured it and linked the chemistry with, you know, some of the toxicological endpoints, you know, so this then becomes a concern. And when you're looking at household items that are being burnt in a wildfire, then these will definitely contribute. So I'm not sure if I've touched on this yet. So where we've been moving is what's called real-time plethysmography, and this is more of Steve Gavitt's work, where we can actually measure lung function during the exposure, and it's really, in my mind, the most sensitive indicator that you can see of obviously irritant responses, you know, but they're also predictive of downstream lung injury. And what we're trying to work out is, can any of this be an early indicator of chronic health effects? So that's kind of where the program's going. Let's see, you need to click and forward. There we go. So this was, let's see, this was, we at this point, because we haven't done the plastic because it explodes and we haven't figured that out yet, but this is the smoldering versus the flaming exposures, filtered or not. So let's see, So here's the plywood and filtered, and here you will see that filtration protects against, you know, the smoldered plywood. Cardboard, not so. So the filtration didn't really work well for cardboard. This is the flaming plywood. We get protection again, and with the flaming, we actually also get protection. Now you will say, wait a minute, here the flaming effect is less than the smoldering. Again, this is this tenfold reduction. So actually there's 10 times less PM here than here, and we're holding it to about the same gas phase. So just to demonstrate again that, you know, we can see pulmonary function changes. You know, we can see the benefits of filtration with some fuels, but not others. And then these other ones are kind of in line with this. This is breathing frequency. This is inspirational time and expirational time, which are just other metrics of lung function, and they kind of show you the same thing. From a lung tox perspective, looking at inflammation, again, we see the plastic and the mixture created the most neutrophils in the lung under flaming. You know, they're depending on the endpoint, LDH, lung injury, a little bit more with smoldering at 24 hours, because we look kinetically as well, either immediately for lung function tests, or we look at 4 hours or 24 hours. And there's a temporality to this lung injury. Typically, you see pro-inflammatory cytokines like here. This is IL-6 come up early, And then you see the neutrophils, which they're signaling in, coming in later on at 24 hours. So again, we're kind of seeing some lung tox, and it's kind of in line with the chemistry and, and the mutagenicity. All right. So where do we go from here? Well, we're going to continue to explore effects of the acute, intermittent, chronic exposures from various scenarios, including these, what I call man-made materials, and just continue kind of plugging away at that. There's a great interest in interventions, whether it's filtration, antioxidants. If I take an ibuprofen, will that help? A vitamin C. Obviously the chemo preventative aspect, does have interest, and with good reason. Another thing that I haven't really talked about is we know that, as the plume travels, if the forest fire occurs in the middle of nowhere, no one's exposed, that's fine. But then when it moves into the greater Los Angeles basin, well, that stuff has aged, and we know that photochemical aging changes the chemistry. And in fact, David DiMarini, my colleague, 20 years ago, published a paper showing that when you photochemically age biomass smoke, it becomes more mutagenic. But that's the only study that's ever, been done. So, just looking at that, and we have the capability of looking at photochemical processing and transport of air pollutants. Let's see. Yeah, and we've been doing this all in mice. There's a big push to not really do this anymore and do experiments on animals. So we've got other systems looking at human airway, cultures and higher throughput. And in fact, high throughput, we're trying to validate some of these assays so that we can, because as you've seen, there's so much variability and potential variables, to study. That it really lends itself to a higher throughput kind of process. But, we need to validate many of those assays and make sure that they're relevant, to what we see in the mouse or indeed the human. And, I haven't touched on this either, but typically we not just study healthy animals, but, we've got animal models of allergy, infection. I did my graduate work on, the effect of air pollutants on respiratory infection. And we've done flu and other, I guess, bacterial pathogens, more recently. But with COVID emerging, people were asking us, well, what about, first of all, does it make you more vulnerable to a potential COVID infection? Or if you have COVID, will it make it worse? So, those are some of the things that, we've done in the past, not with COVID, but with other respiratory pathogens. And it clearly deserves another look. Another aspect is vaccine efficacy. If you're being exposed to all this stuff, we know that tobacco smoke is immunosuppressive, and the vaccine recall and responsiveness to a vaccine in smokers is less. So there's no reason not to think that that wouldn't occur with people exposed to wildfire episodes. One other thing, this is Julia. She's my latest colleague, and Julia is a bioinformaticist. And she's also a pulmonary toxicologist. And, she loves big data. So, we got talking, and she said, you have such rich databases, give me them. And I said, okay, great. So essentially, she takes all of her chemistry and all of her biomarkers and throws them into a program and does essentially very kind of powerful correlation analysis using supercomputers. And she can kind of figure out these chemical clusters and provide linkages or associations with the different biomarkers. So for example, if you look at this one and this one here, we've got turquoise cluster and a blue cluster. So this is, if we're thinking about lung injury and identification of the chemicals that are associated with that, well, here's our neutrophil, in the different, this is a biomass data set. And she was kind of looking across all the different chemical clusters and found that this turquoise cluster that was this metal-rich, kind of set was most correlated with the neutrophils. Whereas with the LDH, lactate dehydrogenase, which I know you guys measure in the blood, but we measure it in the lung as a marker of epithelial cell injury and permeability. And with LDH in the lung lavage fluid, we found that it was more associated with, some of these these organic chemicals, the PAHs and so forth. So it's it's a nice way of looking at it. And as we develop more of these data sets, I think we can provide a lot more of these kind of interesting associations that perhaps will be more definitive in the long run, when we add thousands and thousands of different samples on top of them. And of course, that can have risk assessment kind of, it can inform risk assessment both for individual compounds as well as some of these mixes. So I think with that, I'm happy. I'd like to acknowledge Young-Ho Kim. He's great. He's worked in my lab for about 10 years and done all of the engineering and really manages the day-to-day. But a number of my other colleagues that were mentioned with different data, and our inhalation engineers and chemists and so forth. You really need a good team to make a dent in this. And then I would just like to end by kind of showing you that, and Wayne's going to talk about this in a couple of days, but we're all kind of individual scientists, and we all have our individual programs, but they all kind of meet, and despite it not perhaps being fully planned, we end up with a wildland fire research program at EPA where I lead the toxicology, but we've got epidemiology, we've got modelers, and this kind of crystallized from the grassroots, with different investigators being interested in this, and it kind of was a formational program really from the ground up, which was kind of fun as opposed to having it dictated from above. Anyhow, with that, thank you for your attention. I'm happy to take any and all comments.
Thank you. That was so fantastic. I really appreciate you sharing so much of your work and your colleagues' work, Ian. So we'll just open it up. Please unmute yourselves if you have any questions. I've got a bunch, but I'll let other folks go if they wanted to ask about your presentation. I guess while we're waiting, I'll just announce that, Dr. Cascio, Wayne Cascio, is the director for the Center for Public Health and Environmental Assessment at the EPA. And we've actually invited him to speak on Wednesday. This will be for our Fresno County Department of Public Health grand rounds, but it's on Zoom, so anyone can join, and we'll record that and archive that as well. So everyone is invited from this talk to listen to Dr. Cascio, who's a cardiologist and will be able to offer even more insights about his work, just looking at the human health effects of wildfire smoke. So I wanted to just highlight, I think your mutagenicity testing is really interesting, and the methodology there is called the Ames test, from what I understand, and that's actually something that our toxicology fellows have to brush up on for the board exam. So just keep that in mind, folks, that, these salmonella studies, it's a really interesting methodology. It was developed in the 70s, and it's still considered the gold standard, if I'm not mistaken, for, how you find candidates that end up on the IARC list and things like that. So is that accurate, Ian?
Yeah, totally. I mean, it's a lot of the molecular biologists are poo-pooing it these days, but it's still very predictive for 98% of carcinogens. In fact, as you say, when you mention IARC and when people are doing predictive cancer bioassays, in animals, it's the gold standard for the front line, and it's a fairly simple, straightforward assay. I mean, the utility, that I hadn't realized up until working with David was, you have these different strains that actually have chemical specific, outputs. So, you can actually get a handle on what chemicals are causing it based on the different E. coli or salmonella strain, I should have. But there are other parts. I mean, I'm interested in comet assays and, eukaryotic changes in DNA as well. I mean, everybody wants to get away from the 2-year cancer bioassay, but this is still a very powerful tool. And I think, when you look at the the gradation, across even the chemicals that we tested, it kind of makes sense,
Mhm. Great. And then my second question was about just, you mentioned filtration and how significant that can be for mitigating some of these, maybe not all of these, but some of these hazardous species. What kind of filters are you using? I mean, is it kind of like the HEPA filters that we can go get at Home Depot, or the N95 masks that we're all wearing now in the EDs, or is it that kind of filter?
I mean, well, what we do in the lab is we use HEPA filters, which are, lab based. And, just because, well, we got them and we're dealing with a relatively small stream. I know that people have been looking at some of these homemade things where you essentially take a box fan and then you stick, the 20 by 20 filter on top. And, a lot of these things, if it works at 80%, it's better than 0%, so I would say that, the best you can do is, you're going in the right direction. Obviously, a whole house HEPA filter or some form of HEPA filter, which is 99.99% would be best. The problem with them often is that, they clog up. They are so small. One of the tricks would be to put a roughing filter in front of it. So, kind of like the regular glass, not glass fiber, but the fibrous one, and then the HEPA filter. And you're actually protecting that filter so that you've got this pre-stage. Another interesting thing that, we've been working with in the clinical studies is looking at face masks. And this was kind of from COVID, but it's also working for wildfire and looking at the efficacy, and also face masks that have charcoal impregnated in them, because activated charcoal it takes out a lot of the volatile organics. So when you think about protecting against some of these vapors and carcinogenic materials, then the filter may not do any good because they're vapors, but the activated charcoal may be extremely important. In fact, when we do our animal studies, our clean air animals are typically filtered air, and then the air is run through a charcoal bank, to take away, traffic emissions or things like that. So that's just, I mean, I hope I wanted to impress with everyone that, I've been a PM scientist most of my life, but, this other world of the gases, which are quite often understudied and undermeasured, underappreciated, they are there as well, and they're important. And, and that's just hopefully that you can appreciate that when you look at PM number. Ozone, interestingly, is, ozone's formed from these VOCs. So when you actually have a wildfire, quite often afterwards you'll see ozone go up, and it's because of all these organics and then the photochemistry, which I mentioned early on. So, there are some relationships between those different materials, those organics and ozone formation, which is kind of interesting.
That's amazing. I mean, we use charcoal all the time for, just binding up ingested toxins. So we're very familiar with, some of its properties, but that's very interesting to use it in the air filtration as well. Very cool.
And you can buy it with a bucket load.
Right. Yes.
You bought it at CVS. It probably cost you $100 at CVS, but if you went to Cabot, you buy a ton of it for not that much.
That's amazing. Any other questions for Dr. Gilmour? I just want to say thank you once again. This was just a fantastic talk, and we really appreciate you spending your rainy afternoon with us over Zoom here in sunny California. And I'll send out the link for Wednesday's talk, and in case anyone wants to see Dr. Cascio hear his presentation about the health effects of wildfire smoke. And if anyone has any other questions, then please feel free to relay them, and we could certainly continue the discussion over email.
Sure. Yeah. I mean, if anyone has any issues, my email's in there. It's gilmour.ian@epa.gov. I'm fairly easy to find. So just, shoot me an email and say that you listen to this. I'll be happy to answer it.
Great. Thank you so much.
Okay.
All right.
Thank you, guys. I appreciate the invite.
Thank you
Bye.
so much, Ian. Okay, take care. Bye, everyone.